Hello everyone, welcome. So in this lecture video, we will be seeing one of the pre-processing technique called feature scaling. We will go through what is feature scaling, why we even need to do feature scaling, and how to do it, and some of the precaution steps that we need to take care of while implementing this. So let's start it. So the ML models that we implement, they are used to analyze or identify the patterns in the dataset or to predict the outcome or the target variable. But often the raw data that we have in hand, they're not of useful to directly implement the ML models. So while implementing it, we first need to clean or pre-process the data set. And one of the major steps is the feature scaling issue. So often the features that we have in the data set, they might be on the different scales. So one of the example, if I take whether the loan will be given to a customer or not. So this type of data set might contain the features like age, income, how many family members are there, and whether the customer has previously taken the loan or not, like that. But one of the key features might be like the age and the income. So the age of the person might be vary from like 20 to 80, while the income might vary from like 20,000, 30,000, and it can go even till like lakhs, 10 lakhs, 20 lakhs. So the age and the income are on very different scale here. And if we are trying to predict or implement the ML model on this type of uh, data set, which are on like which have the features which are on very different scale, their income is very much larger number than the age. And if we don't adjust these values, then the income will have much bigger effect on the model than the age, even though both might be important while predicting the outcome or target variable. Here, just because of its high numerical value, income could overshadow the predictive value of the age. And in that case, the model might end up focusing more on the income variable or the income feature because it's large number compared to the age. And it can even ignore the age factor at all. So this is one of the major issue that it can cause the bias prediction also just because of higher numerical value of the age, and it can cause model to misinterpret the feature importance here. So that's why we need to implement the feature scaling. And what it will do, it will put all the features on the similar scale. And in that case, when we have a comparable scale for both the features, the model will also consider both equally when predicting the likelihood for the loan. So let's put down a formal definition for the feature scaling, that it is a way to adjust the numerical data so that all the features will be on same scale. Now let's look at one more example to make our understanding more clear. So it is a house pricing data set in which the features that we had are like age, area, bedroom, stories, and balcony. And the target variable here is price. So suppose we are implementing k nearest neighbor model on this. And how it works is basically it will calculate the distance between each and every data point, and it will select the closest or nearest k data points. Value of k we can decide, and based on the whether it is a regression problem or the classification problem, it will take the average or the majority votes there for the prediction purpose. Now, if we look at here, the data point index 1 and the data point index 2. These two data points accept the area feature value. Other features for these two data points are same. The age is same, the bedrooms are same, the stories are same, the balconies are also same. So intuitively, it might feel that these two should be closer, but if we use the Euclidean distance to calculate the similarity here for the KNN purpose, that is used as the square root of 20 minus 20 square plus 8890 minus 7888 square plus 4 minus 4 square plus 2 minus 2 square plus 3 minus 3 square. If we try calculating this value for the Euclidean distance, this will come around like 1000. While if we look at the case for the data point 1 and the data point 4, even though those two look quite different because the age is like quite the double of it. The bedrooms are also higher, stories are double, the balconies are more in a fourth data point. But just because their areas are closer, that is the feature which has higher magnitudes, these are closer, the distance between the data point 1 and the distance between the data point 4, it will be less than the distance between data point 1 and 2. And because the distance is lesser here between 1 and 4 than between 1 and 2, 1 and 4 will be considered the neighbor here instead of 1 and 2. Even though by looking at the data set, the 1 and 2 might look closer. And here it is creating the problem just because the area has higher magnitude value. But what if we scale the data set? Then what might be changed in the result here? So this is the data set that is obtained after applying the standard scaler on the original data set. Now, I'm not going to calculate the distance here because the values here are like in quite decimal points. So it might be a little bit cumbersome to calculate, but this can be a little bit exercise for you to go ahead and calculate the distance between the data point index 1 and 2 and the distance between the data point index 1 and the index 4th data point. And if we check, then the distance between 1 and 2 now in the scaled version would be less than the distance between the data point 1 and 4 here. And now we can see that the true relationship is coming here, that just because now area is scaled and other features are also scaled, that they are now on comparable scales, this distance or this closeness is actually coming here. And before it was not coming there because of area having higher magnitude value. So it was causing the model to misinterpret the feature importance. Now let's look at the significance of feature scaling here in more detail, that it can make the numerical features comparable in scale. Just now we see that in the previous example, because area was having higher magnitude value, it was creating problems while doing comparison. But if you put all of the features on the same scale, then the comparison also makes sense, because if you want to compare things, you should first put them on the same scale while before doing any kind of comparison. If they're already not on the same scale, then the comparison won't make sense also. And it will prevent the model from favoring features with the larger values. Before scaling, in our previous example data set, the K9 model was giving more importance to the area just because of its high numerical value, that while we were calculating the distances, if only the area is closer, then only it will consider them closer. If the area is area difference is higher, then it won't. And because area has high numerical value, it was dominating in terms of prediction power. But when we scale the features and when we put all of them on the same scale, then area was not given that much high importance than it was given earlier. Now it will put all of them on the same scale. Another significance is the convergence of the algorithm. This is also very crucial part while implementing the ML models, the convergence. And if we do not do the feature scaling, then algorithm may converge slowly or perform poorly. So any kind of iterative based ML models like gradient descent, even though like gradient descent does not always guarantee that it will converge to global optima, but if you do not scale the features properly, then it may converge slowly, that it might take more iteration or more time or more computation power to converge, or it might stuck more in local minima than converging towards the global one. So this last one, we will see it in more details in Colab also. But for now, let's pause here and actually look at the type of feature scaling that we had. So there are different methods in which we can do the feature scaling. We will list out the 4 methods here. So the first one is the standard scaler. The formula for it is for the new feature range, or the new feature would be the previous feature. The mu here denotes the mean of the feature on which you are applying the feature scaling. And sigma here denotes the standard deviation of the feature. And this is recommended for when we want the featured or the scaled data set to resemble a standard normal data set. So it is helpful for the model which assume that the data set follows normal distribution. For example, the linear regression model, which assume that the y given x for the data set follows normal distribution with W transpose X with some sigma. So for those type of models which assume this normal distribution, it is helpful in implementing them. So let's look at this example here and we will implement the standard scaler on this, how we can do this. So let me do it on the feature 1. Similar things can be done on the feature 2 and feature 3 also. So this is our first feature. The mean of this feature would be 1 plus 2 plus 3 plus 4 plus 5. And as there are 5 data points, so divided by 5. So the mean will comes out to be 3. The standard deviation is calculated using square root of 1 minus 3 square plus 2 minus 3 square plus 3 minus 3 square plus 4 minus 3 square plus 5 minus 3 square divided by 5. So the standard deviation comes out to be square root of 2. And as now we have calculated the mean, so the mu that we got was 3 and the standard deviation was square root of 2. If you look at this formula, the feature value here, this 1, will be 1 minus 3 divided by square root of 2. That would be negative 2 by square root of 2. So it would be approximately negative 1.414. For this one, this 2 will transform as 2 minus 3 divided by square root of 2 equal to minus 1 by root 2. And this would be approximately negative 0.707. And just like that, we can transform other values also like 3, 4, and 5. But now if we have to again do the feature scaling for this feature 2, we have to again calculate this mean value here and the standard deviation. This would be different for each feature. So the mean here would be different. We can again calculate the mean in the same way and the standard deviation also and do the same kind of transformation just like we did for the feature 1. So this was for the standard scaler. Now let's look at another feature scaling technique called the min-max scaling. The formula for the min-max scaling is the previous feature value minus the x mean here denotes the minimum value in that particular feature divided by x max. So max here denotes the maximum feature value in that particular feature on which you are applying the scaling, and min again the minimum value in that feature. And it is recommended when you want to bound your feature range within certain range, and the range here would be between 0 and 1, including 0 and 1. So if we look at this example, the same example that we took before, and let's again do the transformation on the feature 1, then the minimum value here, the x min would be 1 for the feature 1 we are doing, and the x max value here would be 5. And if we follow the formula and do the transformation, this 1 will be transformed as 1 minus 1 divided by 5 minus 1, because 1 here is the minimum and 5 here is the maximum, so it would be 0. So for this 2, this would be 2 minus 1 divided by 5 minus 1, because 2 is the feature value, then x min, then x max, and then x min. So this would be 1 divided by 4, so 0.25. And in the same manner, we can do the transformation of these three values also. And for again, just like previously we did, that for the feature 2, you have to again calculate these parameters, like what is the minimum value here. In the feature 2, it would be 50. The maximum value in the feature 2 would be 90. And just follow the formula, we can do the transformation of feature 2 also. For feature 3, the minimum value would turns out to be 120 and the maximum value turns out to be 200. And the transformation will again happen. Like if you are doing the transformation for this value in the feature 3, then it would be 180 minus the minimum value that was 120. So 180 minus 120 divided the maximum value that was 200 for feature 3 and minimum value that was 120. And that would be the new value or the transform value for this 180 in the feature 3. And that's how we can do for the other values also. Let's look at another technique. But before that, we will point out one thing, that both the standard scaler and the min-max scaler, the min-max scaling as well as the min-max scaler, they are both sensitive to the presence of outliers. And we will look at now the method which can be used when we have more outliers in our data set. So that is actually the robust scaling or the median and the IQR based scaling. So the formula looks a little bit complicated here, but let me explain the terms. The Q2 here denotes the median of the data set. The Q3 denotes the 75 percentile, and the Q1 here denotes the 25 percentile of the data set or the feature on which you are doing the scaling. And this is more recommended when we have outliers. More outliers, then we can go ahead with this feature scaling technique. So again, the same example. So we need to calculate the Q2, Q1, and Q3. Q2 is simply median. So for median, first we need to arrange the data set into the ascending order. And if we find the mean of the first feature 1, then the median would be 3. And if we check the 25 percentile for the feature 1, then it would be 2. And the 75 percentile would be 4. And if we follow the formula and do the transformation for the feature 1, the 1 here would be 1 minus 3, that is the median value. Then 75 percentile value was 4, 25 percentile value was 2. So 1 minus 3 divided by 4 minus 2. So it would be minus 1. And if we do the transformation of, let's say this time for this 4, it would be 4 minus 3 divided by 4 minus 2. So it would be again minus 0.5. So that's how we can do the transformation of feature 1. Similarly, now if we do the transformation for feature 2, we need to again calculate these parameters called as Q2, Q1, and Q3 for this data set. And let's say if we are doing the transformation for feature 3, then this Q2, that is the median, would be 160. The Q1, that is the 25 percentile, would be 140. And the Q3, that would be like 75 percentile, would be 180. I'm skipping the step for calculating this percentile. This has been taught in the prerequisite courses of MLP. So for each feature, we have to again calculate these parameters value. And these parameter value are specific for the feature 3 and can be used for transforming feature 3 only. It's not like these parameter value can be used to transform feature 2. That would be wrong. Only for feature 3 we can use. So that was for robust scaler. One more technique that we had is the MaxAbsScaling. So the formula would be that the new feature would be the previous feature values divided by the maximum absolute value. So maximum absolute value we have to take for the denominator here. And it is useful in terms when we have a sparse data set or our features are sparse. So that means there are more like more zeros are there or like more null values are there in that particular feature. Then in those type of scenarios, this max absolute scaling will work. So let's take again the same data set example. So for this feature 1, if you again do the transformation, it would be the max absolute value here would be 5. Now let's take, if I, instead of this 1 here, if we had like minus 10 for this feature 1, then the max value here would be 10 instead of 5 here, because we are taking the maximum absolute value. So that was one thing. And now if we do the transformation based on the original data set only, the max value was 5. And if we follow the formula, the transformation of this 2, for example, would become 2 by 5, that is 0.4. And if we take this 4, then it would be 4 by 5, that is 0.8. Summary of the result for all the feature 1. So this was our original feature 1 value in the example that I took. This was the value of we got after transforming the feature 1 on the StandardScaler dataset. And this was for when we apply MinMaxScaler. If we noticed here, the range here is between 0 and 1. And this will always happen for MinMaxScaler, that the range of the new feature would always be between 0 and 1. For MaxAbsScaler, the range here is 0.2 and 1. While, as I said, that it can go till minus 1 and 1, but here it was not going till minus 1 because we did not have any negative value. But the actual range in which it can happen is minus 1 and 1, but it need not to be always come in between that. So it can be like subset of that range also. And that we had this robust scaler that was suitable for the outlier. So we can see now the spread is actually same. So it is suitable when we have more outlier in the data set. So robust scaler can be used. Again, these are like the recommended uses. It not to always follow. So now let's look at the importance and impact of the feature scaling in the ML models that we had. So the distance-based model. So if we have like KNN model that we initially took the example for, then as we have already taken the example that if we do not scale the features, then just because one or two feature will have higher magnitude value or the numerical value, uh, if only the data points will have closer value in that particular features only, then only it will considered as them close and considered as a neighbor. Otherwise, it doesn't matter what all the other feature values are, only if those particular features which are on higher range, only if they are closer, then only it will consider them as neighbor if we do not scale the data set properly. So it will not weight them equally in that case, and it can result in a biased result because one feature or some of the feature which have higher magnitude value will dominate in that case. So this is the impact that might happen. For the support vector machine algorithm, it will also rely on the distance of calculation because it finds the hyperplane or a line which separates the two classes. Um, so it should have like maximum margin. So it's also rely on the distance. Also, when we are doing the transformation of data set using RBF kernel, the RBF kernel is also like exponential of minus distance square divided by sigma. So this is like the RBF kernel formula for the transformation. It calculate the similarity between two data points using the distance based again matrix. So if again the uh, data points for the features are not scaled properly, then again this will impact the distance based calculation. Hence, it might also result in biased estimate or it might perform poorly. Then there's dimensionality reduction techniques called PCA. So if we have one feature which is like on higher range, then the variance in that for that particular feature would be very high because the range would be high. So if we have a like higher magnitude feature, although this is statement might not always be true, that just because the higher magnitude are there, then the variance would be high. Only if the range of that feature would be high. So there might be chances that when we have high magnitude, there are chances for it to have higher range also. So that's why in that case the variance might be high. So again, it will not give equal importance. So we have to scale the feature in that condition also. So that just because of higher magnitude feature, it does not consider the variance to be high just because of that. Now let's come to the gradient based model. So to ensure a smooth convergence or to lead to the global optima and also to converge fastly, we have to do feature scale. Now we will look at this image here that in the first image on the left side, both the features are not the same scale. And this is the contour plot for the gradient descent that how our algorithm are converging to the optima. So because one feature has a high value, it is making the gradient to oscillate. So that's why the convergence are like in this zigzag manner and it is taking more iteration and it is also not a smooth convergence here. But when we put both of them to the same scale, then the convergence here would be more smoother, faster. So for a smoother convergence and the faster convergence, and also to make it reach to the uh, global optimum, although it is not always necessary, but it can affect the performance also. We need feature scaling for the gradient-based model also. For example, the logistic regression. And the another models that we had are like the tree-based model. So these are the models which have a less or minimal impact in terms of feature scaling. So the examples are like the classification or the regression tree or the random forest. So let me quickly take one example of again the age versus income data set. So how the decision trees will be formed like based on the answering question. So the question would be like whether the age is less than 50 or not. So age is less than 50 or not, and that's how it will keep on growing. And then whether let's say the income is less than 50,000 So that's how the tree will be keep on growing based on these questions across different nodes. And in that case, the feature scaling does not have much impact because uh, is that asking the question, and in terms of that, it does not have that much impact on the what is the magnitude of the features actually. So this is like a yes or no type of question, so it does not have that much impact. So in this type of model, if you are implementing, then feature scaling might not have that much good impact than compared to the other models. Now, some of the common pitfalls and best practices while implementing this, that when it is not necessary to the scale features. So the feature scaling is very important. If it we say while implementing any ML model, we should always try it, but there's no absolute necessity that it will always boost the performance of the model. That if you implement the feature scaling, it is not always necessary that it will improve your score or it will lesser your error. So it will not always guarantee you the best result. However, it will improve, but it might happen that improvement is not that much or it does not improve at all. So the cases where it does not make much more impact is the tree-based model that we just discussed, that all the tree-based model are almost unaffected by scaling. So in those type of implementation of those models, we can skip this part, but rest of them, it's like a trial-based process. We have to try it out, and based on that, we can check whether the improvement is happening or not. Now, the next thing is avoiding data leakage while scaling. So what does this mean is basically while implementing the ML models, we do not want our model to come in contact with a test data set because it is used to have a check the quality of the model. So that is the data leakage that if your test data set by any chance or any mistake, it comes in contact with the model. And it can happen while implementing the feature scaling part, that is this. So it's a code snippet that is given to us in which we implement the standard scaler on the digit dataset. And we should always do the fit methods, that is the learning parameters method on the training dataset. So the parameters for the standard scalars are basically the mean and the standard deviation. So those parameters should always be learned on the training dataset. And the way we learn those parameters are using the fit method. So we should always use the fit underscore transform method only on the training dataset. And on the test dataset, we should only implement the transform method. We should not use fit underscore transform method on the test dataset, because what this will do is it will actually again recompute all those parameters to do the transformation. But we do not want that, because in that way, it will be a data leakage problem, because the model will come in contact with the parameters for the test dataset also. So it might give the bias result. So that's why parameter for the scaling should be learned only on the training data set, and we should only use the transform method while doing the transformation of the test data set. The last line for this code snippet is wrong. We should only do the before the second last line, that is scalar.transform x test. And one more pitfall for this is the loss of interpretation. So when we do the scaling for this example that we had before, if we look at the values of age after this transformation, it comes out to be negative. The area is also negative. Bedrooms, all of them also are negative. And of course, the negative age, the negative bedrooms area, these quantities does not make sense or meaningful in the real world context. There's no meaningful thing that we can interpret from the negative area. So after scaling the feature, they lost their true meaning, and it becomes more harder to explain the context there. So this is also one of the common pitfalls for the feature scaling. The key takeaways about the feature scaling part, that now we know that feature scaling is very important and crucial steps, but it does not need to always improve the performance of the model. And it is especially crucial for the model that relies on the distance-based calculation like SEM and KNN, and also for the gradient-based method like logistic regression for a faster and smoother convergence. For KNN, of course, if the distance is calculated. If one feature is on high scale, then it will dominate the performance there. And for the tree-based model, we know that because it is based on like yes or no type questions, so the scaling here does not improve the performance that much. So in those type of implementation models, we can skip this part. And we have to avoid the data leakage. That is, we should only use the fit underscore transfer method on the training data set. We should not use it on the test data set. Test data set should be transformed using the transform method only. Parameters should be learned on the training data set only. That is learned using fit underscore transform method. And there are different scalars that we had. Different scalar technique we saw: StandardScaler, MinMaxScaler, RobustScaler, MaxAbsScaler, and they all have different purposes. So, and there's no such techniques which can actually choose us to select the right one, although we have listed out when what is the key recommendation, like for StandardScaler, when we want the data to behave normally, standard normal. For the min-max scaler, when we would want the data set to be within certain range. MaxAbs is useful for the sparse and robust scaler for the outliers. But still, it is not always necessary that when we have more outliers, we should always use the robust scaler. It might happen that standard scaler might work there. So there are different scaling technique we have. We have to do a try and test every time. There's no such technique which can actually tell us which is the right one to use. So it's all about experiment. Always experiment with different scalar, and we have to evaluate their performance, and we have to find out which one is performing for best for your data set. So that's all for the slides. We will now move on to the collab and look more there.